Okay guys, here is my first attempt at helping you guys with your homework via a video. So if it's a little shaky, you gotta bear with me a little bit. So this is for the 3.9 homework online. So you should be following along with me. As you look along with this, it'll look similar to what you see on the screen. So number 1 says, use the distributive property to write each of the following expressions as in equivalent form. Remember, equivalent means just equal. So the distributive property says that basically this guy, remember, has to jump the fence. So this guy, ignore this. If he jumps the fence, it becomes 2 times 7. And if he jumps the fence again, it becomes 2 times 3. And you bring your plus sign in the middle. And so you end up something that looks like that. Now the second one here, if you look at it, it's almost like the guy has already jumped the fence. Notice that the 5, if I pull him out, if I came at it the different way, it would look like 4 minus 7. He's already jumped the fence and you have to take him out. The next one, the 3 needs to jump the fence. So if he jumps the fence and lands on the x, he's going to look like 3 times x. Then he's going to jump the fence again and hit the 4, and so he ends up with 3 times 4. Bring over your plus sign, and you're done. Again, this guy you need to go backwards. The 6 has already jumped the fence. See how he's there twice? He landed on both the 2 and the 4. So pull him out. Leave the 2 and the 4 in the gates. And see this plus sign? Plus sign comes back over. All right, so that's the first question. The second question says that we have to, which of these graphs matches the input-output table? So you can think of these as 3, 1, 5, 2, and 7, 3. Remember that when you have a coordinate pair, the first coordinate tells you to go left or right, and then from there, you go up or down. Sorry. Up or down. So we have to find the graph that has 3, 1, 5, 2, and 7, 3 on it. So let's look at the first graph. So I like to go ahead so I can see it and fill in what I see here. So it should have 3, 1. So let's check 3, 1. If I come over 1, 2, 3, and up 1, there should be a dot right there. Doesn't have that dot, then it's not the right graph. Let's try B. Come over 3, 1, 2, 3, up 1, doesn't have a dot, not the right graph. Let's try C. Come over 1, 2, 3, up 1, so the first one works. So we're supposed to have 3, 1, check. The other ones we're supposed to have are 5, 2, and 7, 3. So let's check 5, 2, and 7, 3. If they are all there, then we found the matching graph. So we come to the right 5 and up 2. That's there. And then 7, 3. 1, 2, 3, 4, 5, 6, 7, up 1, 2, 3. They're all there. And so you have the correct graph. This graph matches this input table. It's got the same points on it. All right, next one, moving right along. If you follow the same pattern of adding squares, how many squares do you need, let me make some room, to build the 100th term? Well, my first thing is I'm going to make a table. Definitely make a table. So if I make a table like this, here's the term number. Here's the number of squares. So we've got term 1, 2, 3, and 4. 1, 2, 3, and 4. Number of squares in term 1 is 2. The number of squares in term 2 is 3. The number of squares in term 3, 1, 2, 3, 4 squares. In term 4, 1, 2, 3, 4, 5. And we need to know how many squares do you need to build the 100th term. So I need to basically figure out if I made this guy, I want this guy to be the term number to be 100. how many do I have to go there? Well, if you find a relationship between 1 and 2, the input and the output, the term number and the number of squares, you see that all you do is add 1 to the term number to get the number of squares. Add 1, and you get the number of squares. Add 1, you get the number of squares. So if we wanted to know the number of squares, it would be 101, D. Next one. What rule relates the term number T to the number of tiles in the pattern? Now they're talking about the same problem we did over here on 8. So all we did is we took the term number and we added 1. So if we had to write this out in English, we'd start with the output, which is number of squares is always equal to, number of squares is always equal to the term number plus 1. Well, in the problem, it tells us that the term number is now going to be represented by T. And the number of tiles in the pattern, number of tiles in the pattern, number of tiles, number of squares, is N. Bring down your plus 1, and there's your rule. The number of squares is equal to the term number plus 1. So you get D. Courtney made the following pattern. What rule will tell you how many white hexagons, W, so my hexagons, the number of white hexagons is W, are needed for any given number of black hexagons? So let's make a table again. If you take a look at our choices here, W is always on the left, and so that lets us know that W is always going to be our output. Remember, it always starts with output. The equation always starts with the output, so we know that W is the output, which goes on the right-hand side. Now it says are needed for any given number of black hexagons. So B is our input. So we've got black hexagons here, and we've got white here. So what rule would tell you how many white hexagons are needed for any given number of black hexagons? So when there's one black hexagon, there's 1, 2, 3, 4, 5, 6 white. When there's 2 black hexagons, there's 1, 2, 3, 4, 5, 6, 7, 8 white. When there's 3 black hexagons, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 white. So now I'd go ahead and pause this and see if you can come up with the relationship between here and here. What can I do mathematically to get from here to here every single time? Okay, so you should have come up with, we can multiply it by 2 and then add 4. 1 times 2 is 2, plus 4 is 6. If we multiply it by 2 and add 4, 2 times 2 is 4, plus 4 is 8. If we multiply it by 2 and add 4, 3 times 2 is 6, 6 plus 4 is 10. So every time, to get the white, we take the black number, multiply it by 2, and then add 4. Again, to get the white number, we take whatever the black number is, multiply it by 2, and then add 4. So you get W is equal to 2B plus 4. Remember Matthew, who plays on the school baseball team. Matthew often does warm-up drills in which he throws the ball up in the air and catches it when it comes down. The table shows some data about one particular throw. So remember that this is always X, and then Y is over here. The table shows some data about the particular throw. Which of these graphing windows would help get a good picture of the throw data? Well, the lowest X is 0.0. The highest X is 1.5. So the X should be in the middle. Somewhere X should always be between 0 and 1.5. The lowest Y is 7. The highest y is 16. We always want to start with